Hello, how are you doing? Oh, you're muted.
No. Okay, that's better, huh? Thank you. How about that?
Yeah, we can hear you.
Great. Thank you, Ashley, right?
Mm-hmm.
Okay, cool. All right, I'm gonna give everybody a second to be thinking about these really challenging brain exercises while everybody's joining up the room. This is trying to refresh and remind everybody about what we were talking about during our last class together, and then we'll get into what we're going to talk about today. So think about these couple of questions as everybody's joining, and then we'll kind of go through them together. Okay, so what kind of bond will you guys get if you combine two s orbitals together? Is it going to be a sigma bond or a pi bond? What kind of bond is it going to be?
Pi bond.
Well, think about two s orbitals and what they look like coming together, right? So they're going to be coming together and overlapping directly between the two nuclei. And so those two s orbitals are going to create a sigma bond. Someone's asked if we have a quiz. The quiz is on Friday. Okay, so anytime, just kind of a refresher and a reminder, sigma bonds are what happen when the electron density is between the two nuclei on that internuclear axis. Pi bonds are what happens when that electron density is above and below that internuclear space. So remember, a sigma bond is like the hot dog, and a pi bond is like the hot dog bun. Okay, so now thinking about that, if you bring an s and an s orbital together, they're going to overlap in the area between the two nuclei. So you're going to get a sigma bond. What about if you bring together an s orbital and a p orbital? What kind of a bond will you get?
Sigma bond.
Yep, a sigma bond here too. So it turns out that s orbitals are typically, I think I can go ahead and say all the time. For this class, sigma bond, for this class, s orbitals are always going to be participating in sigma bonds for this class. There might be some exceptions in other classes, but for this class, those s orbitals are going to participate in sigma bonds. What about if you want to combine two p orbitals together? What kind of a bond are you going to get?
Pi bond.
Pi bond. Anybody else? Is everybody agree? Bond? If you're bringing two p orbitals together? Okay. Is that the only kind of bond you can get if you're bringing two p orbitals together?
No, it would be a sigma bond as well.
Yeah. So it turns out this is kind of a trick question, the third one, because you don't actually have enough information to answer this question as it's written. If the two p orbitals are coming together in an orientation where they're parallel to each other and they're coming on side on to each other, you will indeed get a pi bond. That's correct. However, if your two p orbitals are actually pointed like head on towards each other, like a head-on collision, those, because that will result in electron density between the two nuclei, those two p orbitals will make a sigma bond. So you'll be able to see that if you review your slides from the last class. But if I'm asking you about combining two p orbitals, I have to tell you what orientation they're in relative to each other. Or you have to say, well, they could make a sigma bond or they could make a pi bond. Does that make sense? Okay, so all right, just a reminder for everybody, there is an SI session today. Also, I just found out like minutes before class, so I haven't even made any changes or postings about this. I have to shift my office hours today. So my office hours today are not happening at this time because a meeting has come up that I have to be at. And instead, my office hours are going to be rescheduled. I need a minute to figure out when to put them. If it's not later this evening, so the SI session is from 5 to 6. I may have some this evening, but more likely I'll post through an announcement that there will be some office hours tomorrow that you guys can join into. So I'm sorry about that last minute change, but it was a last minute change for me too. So I'll make sure to get you guys some office hours, and don't forget, you can also please go to the SI session. I believe it's in Hibbs 118. All right, the same announcements as last time. We are coming up on your first due date for your homework, which is for chapter 1. It's Monday morning. And also, as you guys know, we're going to have a quiz on chapter 1 that will be in class. It's going to be about 10 questions, mostly multiple choice. There might be a fill in the blank or short answer or two stuck in there. I haven't written it yet, so these are all kind of a ballpark, just to give you guys a sense. I'm not saying this is what it is set in stone. I'm going to use Canvas to deploy the quiz, so you'll be able to find that quiz in Canvas. For this quiz, we're not going to use the Respondus browser because I'd like to have everybody test that they can use it first before we put something with a point value on it. In future quizzes and tests, we will use the Respondus browser, but for this one, we will not. It is, however, still closed book, closed notes, closed off from other people, closed off from the internet. So it is on your own, out of your own head, that you will need to study for. We are taking it during class, and MC stands for multiple choice. So the way this is going to work for taking it during class, the way I did it last semester, which seemed to work very well, is that you guys will log into your quiz right at 1 p.m. and it'll be a timed quiz. And then after you finish the quiz, you come on into the Zoom room and we'll finish up the class with lecture. So the quiz will have a set time period, probably 15 or 20 minutes. And then when you finish the quiz, you come back and meet me here in the Zoom room, and we're going to start it on chapter 2. So we will still use the class time. We will use the full class time, and the quiz is only going to be a portion of it. Okay.
So we don't have to be on Zoom during the quiz.
You do not have to be on Zoom during the quiz. No.
Okay.
Okay. All right. Oh, and one more announcement that I should have put up here, and I'll try to remember to put up here before class. Please take a moment before Friday and read the part of your syllabus that talks about technical difficulties during a quiz or test. That's an important thing that is listed in the syllabus and you're responsible for being aware of. Okay, so here was where we are in chapter 1. We are going to finish chapter 1 today. Someone's asked in the chat box, are we able to go back to previous questions? The answer is yes, but sort of. So please read your syllabus about this. I ask you guys to answer every question, put in an answer for every question in the order that they are coming up on the screen. If you have time left at the end, you can go back. Now, the reason I'm saying it this way is because if there's a technical difficulty and you get booted out of the quiz or test, you will be graded on the answers that you put in already, and anything you haven't answered, I'll reset it for you and you can answer those. And this, you can backtrack, but read your syllabus carefully. This is the only mechanism that I have to make it fair for you guys and limit cheating, the type of cheating where somebody looks at all the questions and then oops, has a technical difficulty, and then looks up all the answers to all the questions and then comes back in and answers all the questions. So really, the truth is you're only cheating yourselves if you cheat. And so I try not to stress out too much about cheating. But if I have a way that I can see, there's a logbook that records how much time you spend on each question. And so if I want to, I can go in and look at that and see, and like I can tell if people are cheating. So don't cheat. That's the easiest way to do this. But please follow the instructions on the quiz or test and on the syllabus by putting an answer in each one. Even if you're not sure about it, put down your best guess. And then if you have time at the end, go back and look back at those ones. Okay, so yes, you can backtrack. Yes, it is timed. And the quiz questions are not really going to be similar to the homework because the formatting of online quizzes is just that it's going to have to be multiple choice mostly, or else it would take too long for you guys to do. I didn't answer about the periodic table already. That's a good question. I will have a periodic table provided for you that you can link to from within the quiz. If you want to have the one that I emailed out to the class printed out next to you, I'm okay with that. Also, I should say this, and I really should update the syllabus to say this. if you want to have scratch paper, blank scratch paper, blank scratch paper for when you're doing the quiz or test, that's okay, but it has to be blank paper. Okay. But no notes, no book, no outside resources. All right. Let's go ahead and get into chemistry land. Oops, I went the wrong way for chemistry land. And we're going to finish up chapter 1 today. So we just got a little touch of hybridization on Monday. And I'm sorry, guys, by the way, I think I was talking on Monday as if it were Wednesday. What a Monday it was for me. Today is Wednesday. Today you have an SI session at 5. Regarding, sorry, someone's asked in the chat box about calculators for the quiz. You will not need a calculator, and there's a calculator function on the quiz. So the answer is, you have access to the calculator and the thing, so you shouldn't need your own, okay? Okay, so for hybridization, one of the things that I wanted to do is give you guys, so last time we sort of just got to SP hybridization, and I wanted to take a moment, take a step back and give you guys an overview of where we're headed with hybridization, show you all 3 of the hybridization styles or types, and then go back and dig into each one in more depth. And I think for you guys being able to see where we're headed will help you actually even make connections and draw parallels between the different things. So the first couple of slides I'm going to show you are the same as the ones I showed you on Monday. But basically the reason that we are in here talking about hybridization is because we can't explain the geometry of real life molecules using just the S and P orbitals that we know about, right? So the P orbitals that we know about are all pointed in 90 degrees relative to each other. And so if we're only allowed to make molecular orbitals that point in the same direction as our atomic orbitals, we can't possibly explain the bond angles that we see in molecules like ethylene or methane, or really pretty much any molecule out there has bond angles that are not explainable by S and P orbitals alone. So what hybridization does is it allows us to resolve our atomic orbital theory with what we actually visualize and experimentally can determine in real life. And the connection here, the intersection here, is something called VSEPR, or valence shell electron pair repulsion theory. And it sounds like a big word, big term, but it's really straightforward if you break it down and look at it. We're talking about the valence shell, so valence shell electron pairs. What are the types of valence shell electron pairs you can have? Well, you can have them in a sigma bond, you can have them in a lone pair, but that's what we're essentially talking about, is how these bonds and lone pairs, because they all are negative charged because they're made up of electrons, they repel each other and they try to get as far away from each other as possible. And this is one way that we're going to use to help us bridge this kind of theoretical gap here and help us explain the actual real life shapes of molecules. So we talked last time about SP hybridization, right? And I just want to remind everybody, when we're talking about hybridization, we're talking about taking atomic orbitals on one atom and hybridizing them, and those are then the hybrid orbitals on that same atom. We haven't involved any other atoms yet. We're only talking about what's happening to the atomic orbitals on an atom, any atom. So SP hybridization is what happens when you have an atom that needs to create bonds to 2 other atoms. And so in order to create bonds to 2 other atoms, we're going to need 2 orbitals for those bonding interactions. And so we're going to take 2 orbitals to create our hybrid orbitals, the s orbital and the p orbital. And then, of course, because of conservation of orbitals, we are going to get out 2 orbitals, a hybrid orbital with a major lobe pointing off to the right and one with a major lobe pointing off to the left. Now, I'm showing these separate from each other, but in real life, they're superimposed. That black dot is the same nucleus as that black dot, which is the nucleus of the atom we're talking about. So you can see how our hybrid orbitals have characteristics of the atomic orbitals that made them, right? So they have a directionality associated with them that comes from the directionality of the p orbital. The s orbital doesn't really have a directionality, so it's kind of like the blood type donor O. It's like the universal orbital, right? So you don't really get any directionality information from an s orbital, but you do from a p orbital. And so it's that directionality of the p orbital, the orientation of the p orbital. That's why we have a hybrid orbital that kind of points off to the right and one that points off to the left. Okay, so we'll go, like I said, this is a summary slide, and so we're going to go into more detail about each of these on the next couple of slides. But what if we need to bond to 3 other atoms? Well, if we need to bond to 3 other atoms, we want to spread those 3 atoms as far apart in space as we can. And so to do that, we're going to combine 3 orbitals to get 3 hybrid orbitals. So we're going to, in this case, create what's called sp2 hybridized orbital set for the s and the px and the py that we're bringing together. So sp2, because there's 2 p orbitals coming into this play. And you can see when we do this, when we combine these 3 orbitals together, if you kind of mix them all up and get a weighted average of their areas of combining and in positive and negative ways, this is what you get. You get 3 hybrid orbitals. They're all sp hybrid orbitals, and they point out in 120 degrees from each other. Now, each of them, each hybrid orbital here has a major lobe and a minor lobe, and that is accounted for by the different phases of the p orbitals and how they intersect with each other and with the s orbital. The other thing to note here is, if you think about it, these 3 orbitals have features that came from the 3 orbitals that made them. So for example, the px and the py orbital are planar with respect to each other. They're in the same plane as each other. And it turns out that all of the sp2 hybrid orbitals are also in the same plane. And this should make sense, because if you look at these 3 orbitals that I'm showing you, none of these orbitals really sticks out too much in front of your slide or behind your slide, right? They're all pretty much in the slide. Of course, they have, they're 3-dimensional things, so they stick out a little bit, but they're not pointed in or out of the slide here. They're all in the plane of the slide. And so indeed, when we hybridize them, all of the hybrid orbitals are also going to be in the plane of the slide. Okay, and finally, to round this out, if we need to bond to 4 other atoms, which is what carbon usually likes to do, carbon and other atoms as well really like to bond to 4 things. And so we're going to need 4 hybrid orbitals to do that, to spread those 4 things out as much as possible. And so we're actually going to take all four of our valence shell orbitals, the s orbital and all 3 of the p orbitals. And we're going to combine them and mix them all up together. And what we're going to come out with is this kind of weighted average that looks like a balloon animal over here that has 4 hybrid orbitals. There's one pointing up and one pointing sort of down and to the left. Those are in the plane of your screen. And then here to the right, you have one pointed out of the screen and to the right a little bit, and one pointed back behind the screen and to the right a little bit. And the process here is done so that these orbitals and the things that they're bonded to can get away from each other as much as possible. And if you think about like classical Greek geometry, that means that 109.5 degrees is as far apart as these 4 things can get from each other. If you tried to get 2 of them farther apart than that, then they would end up getting closer to something else. Okay, so this is kind of the overview of hybridization. We have 3 different types here that we can access, depending on how many other things that we need to bond to. So what that means is that this is also going to tell us something about the shape of the molecule in that region. And if you have sp hybridized and you're bringing in these 2 orbitals and making these 2 hybrid orbitals, you can see the orientation is going to be out to the right and out to the left based on the p orbital that came in. And so that's a linear geometry. Likewise, with sp2, you have 3 things sticking off in different directions, but they're planar because of the px and py orbitals being planar. So the geometry you'll get is trigonal planar at that whatever atom center that is. And finally, for sp3, you would get tetrahedral geometry with things sticking off in 4 directions. Okay, So I'll drill down into each of these and show you some examples of each over the next couple of slides, but there's one more thing I want to note here, and I'll update my slides before I post them to reflect this. I've left a big concept out of this slide for simplicity's sake as I'm introducing it, but it's not just bonding to other atoms that we need to account for. It's VSEPR theory, so valence shell electron pair repulsion theory. So we also need to account for if the atom in question has a lone pair. So to be technically accurate, this over here should really say need to bond to 3 other atoms or lone pairs. And then you would still need 3 orbitals. And we'll see some examples of that as we go on. For the moment, as you guys are learning these hybridization concepts, I want you to stick to thinking about how many other atoms you need to bond with, but then just keep in mind we'll have to stretch this out to accommodate lone pairs as well. Okay, so, and then this is my reminder that these are, everything on the slide is an atomic orbital still. We're only talking about what's happening at an atom. It could be a carbon atom, it could be an oxygen atom, it could be a nitrogen atom, it could be a phosphorus atom. It doesn't matter. But we're only talking about what is happening at one nuclear center and the atomic orbitals that atom owns. We're taking the S and the P original ones that we know it owned from like original theories, and we're mixing them up together to create some hybrid and maybe some leftover unhybridized. Then once we've hybridized them, those hybrid orbitals can then participate in molecular orbital bonding. Okay, so we talked about this last time. This picture is showing again molecular orbital bonding up at the top here. So if I'm bringing a p orbital and an s orbital together from different atoms, then they'll come together to make a bonding orbital and an anti-bonding orbital. Remember, conservation of orbitals. What we're talking about in hybridization, again, is combining atomic orbitals on the same atom. So this is just my slide to kind of drive that point home about the difference between molecular bonding, where we're bringing atomic orbitals on 2 different atoms together to make a bonding and an anti-bonding, versus hybridization, where we're bringing together atomic orbitals on the same atom to form new atomic orbitals that are hybridized, and then they can go on to make bonds with other atomic orbitals on other atoms. Okay, so here is another look at the SP hybridization. I think I showed you this. I showed you guys the slide on Monday, but I think we were rushing a little bit at the end. So I just wanted to put it up again. As we know, we have to get the same number of orbitals out as what we bring in. So in this case, SP hybridization, we're bringing together an S and a P orbital, and we have 2 different options for how we can bring them together, and indeed they both occur in sort of a statistical mixture of the 2 options. So if they come together one way, they'll get you orbital density off to the right, and in the other way, orbital density off to the left. But again, these are superimposed on each other. They're both happening on the same atom. And you can see by the directionality of our new hybrid orbitals that we're going to get new bonds that are pointed in that direction that's 180 degrees from each other. So this is a case of the molecule acetylene. And now this should also make sense with what we've been thinking about in terms of this carbon here on the left. How many things is it bonded to? Well, it's bonded to 2 things. 1 hydrogen atom over here and 1 carbon atom over here. Does not have any lone pairs that we have to account for. So this carbon atom is only going to need to hybridize 2 orbitals to account for its 2 bonding partners. And this is just your reminder that all of these black dots are representative of the same atom's nucleus right now. Okay, so let's put it in a molecule. This is going to be a sketch of the bonding of beryllium dihydride. So beryllium is in the second row of the periodic table. And if our beryllium wants to bond to 2 hydrogen atoms, if we make a Lewis dot structure of beryllium dihydride, we'll find out that that beryllium does not have any lone pairs. And so it doesn't have any lone pairs and it wants to bond to 2 things. So we need to use 2 atomic orbitals to create those hybrid orbitals for those bonds. So we're going to put together our S from beryllium and our P from beryllium to make an SP pointed to the right and an SP pointed to the left on beryllium. And if you look over here on the superimposed picture, look only at the purple part right here. That'll give you a picture of what is happening at the atomic orbital level of the beryllium, right? So this beryllium has now hybridized its S and one of its P orbitals together to make the SP orbital pointed this way and the SP orbital pointed this way. And each of those is going to participate in making a new bond with hydrogen, with the 1s orbital of hydrogen. And I just want to point out here that the hybrid orbitals have this little back lobe that's an opposite phase. They're still there. We just don't ever draw them in kind of bonding sketches because everything would get really busy. So we just don't bond them. Someone's asked why beryllium has an S and a P orbital. And it has an S, it actually has the same orbitals as carbon does, right? Every atom in that second row of the periodic table has a valence shell that has a 2s orbital and 3 2p orbitals. So just because there aren't electrons in those orbitals doesn't mean that those orbitals aren't there. Okay, so beryllium has an s orbital and 3p orbitals, and carbon has an s orbital and 3p orbitals, right? So they have these orbitals, they just might not have electrons in them, in their native configuration. Did that answer your question? Okay, so let's move on to sp2 hybridization. So this is going to be the case where you have to bond to 3 other atoms or accommodate 2 bonds and a lone pair. And so in order to do this, we're going to want to bring together 3 atomic orbitals. We'll always take the s orbital, and we'll take, in this case, the px and the py. And so when we combine those together, what we get out is this kind of a weighted average that looks like this set of sp2 hybrid orbitals, where each one has a bigger lobe and a smaller lobe, and they're pointed in 120-degree directions from each other. So this gives us our 120-degree bond angles. Again, that's the biggest bond angle that you can have for 3 points on a sphere. If you try to put 3 points on a sphere, they're going to be 120 degrees apart from each other. And if you try to move any 2 of them farther apart, then they would get closer to the third. So what this looks like when we actually superimpose it is that these 3 hybrid orbitals, of course, we're talking about all on the same atom, just like before. So we have to look at them and consider them superimposed. And then it becomes a little bit easier to see the 120-degree angles. It also becomes easier to see this trigonal planar geometry. And just a reminder, it's planar, right? Because our hybrid orbitals have to retain some of the characteristics of the orbitals that they came from. And so the x and the y, px and py orbitals are in the plane of your screen. And so all of the hybrid orbitals stay in the plane of your screen as well. There's none of the orbitals coming in that were pointing out or pointing behind the screen. So we don't have any hybrid orbitals pointing anywhere but within the plane of the screen. Okay, hopefully that makes sense. Let's try it. So this is not for you to upload. This is just a problem for us to work through and talk through together. But I want everybody to take a minute and try to, first of all, draw the Lewis structure for borane, which is BH3. And once you draw the Lewis structure for borane, I want you to take a minute and think about what hybridization the boron would need to be and what the bonding diagram might look like. So you can sketch out a little cartoon version of the bonding diagram for this molecule. Think about that on your own for a minute, and then we'll talk through it all together. And as you're drawing your sketch, you don't have to worry about the little small back lobes of any hybridized orbitals. If I don't have to do it, you don't have to do it. Okay, how are we doing? How many total electrons are there in this system? 6. Great. What does that mean for boron? Is it going to have a full octet? No, it can't, actually. It can't have a full octet. It's not breaking the octet rule, though, because remember, the octet rule just says that every atom tries to get a full octet, just can't go over the full octet. All right, so what does that look like? Here's what it looks like in Lewis dot format. I prefer, again, for you guys to use regular Lewis structures that show the bonds as lines, but I took this from your book and they're using dots. So there are indeed only 6 valence electrons in borane. And so what that means is that boron has a single bond to each of the 3 hydrogen atoms. So if boron has to bond to 3 different hydrogen atoms, then we need to create 3 hybrid orbitals to accommodate for that. So what's the hybridization of boron in borane? Okay, good, sp2. That probably was obvious coming on the tail end of the slides that we just did, but that's all right. Okay, so based on Vesper, our 3 bonds should mean that we need hybridized orbitals to maximize the distance between those 3 bonds. And so we are indeed going to be an sp2 hybridization motif. We're going to have 120-degree angles. And what that looks like in terms of a bonding sketch is something that looks kind of like this, right? So we've got our sp2 hybridized orbitals that are pointing out at 120 degrees from each other. And each of those hybrid atomic orbitals can then be used to overlap with a hydrogen 1s orbital to create those bonds. Don't forget, just a reminder, what's not shown in this picture here is the pz orbital that is empty, not having any electrons in it, and it is sticking out perpendicular to the screen right in the middle here. It's unhybridized. It's just like a spectator orbital in this process. Okay, cool. So with that said, let's go ahead and knock out, actually, there's a question, so I'm gonna go back. So part B, draw a diagram of the bonding of the molecule and label the hybridization of each orbital. So we figured out that we need to have sp2 hybridization because there are 3 bonds. Let me rephrase that. Boron is bonded to 3 different atoms, right? So if boron is bonded to 3 different atoms, then we're going to need to accommodate 3 things with our hybrid orbitals. So we'll have 3 hybrid orbitals. There's no lone pairs on boron, so we don't have to worry about that. So what I've asked for is a sketch of the bonding in the molecule. And so the bonding in the molecule is the orbitals that are participating in the bonds. So we know the boron has hybridized its orbitals to be able to participate in bonding. So it has these 3 orbitals. Those are the boron's atomic orbitals. And then each hydrogen atom has a 1s orbital that is bonding with the sp2 hybridized orbital on boron. So someone's asked in the chat box, does that mean we have to add that p orbital or not? So it depends on how I ask the question. So technically on this question, I've asked you to draw a diagram of bonding, and that p orbital, that leftover pz orbital, is not participating in any bonds, and so it's not drawn here, and so technically that is correct. But it's still there, right? It is still there. Okay, so someone's asked in the chat box, say it was BH2 and it was only bonded to 2 atoms, it would be sp. And the answer is it depends if it is, so BH2 neutral, BH2 positive, so it depends on, we would need to know the total number of electrons in the system. And if it was BH2, let me think about this. If it was BH2 minus, then it would have a lone pair, and then it would still be sp2 hybridized. It would have an sp hybridized orbital for each of its hydrogen bonds, and the 3rd sp orbital would be used to house a lone pair. If it's BH2 plus, then you would have a total valence electrons of 4, and you would have Is that right? 3, yeah. So you'd have 4 total valence electrons, and you would have no lone pairs, and in that case, it would be sp hybridized. So it really depends on the total number of electrons in the system.
So does that mean if we don't have any electrons, like any lone pairs out, it's just the orbitals, basically you just count how many atoms it's connected to, and then that's what it is. So if it's 2, it's sp, if it's 3, it's sp2, if it's 4, it's sp3.
That's exactly right.
Okay, thank you.
You're welcome. Okay, someone's asked about if you'll be asked to draw the diagrams on the quiz, even though it's multiple choice, or just label. I'm not going to tell you what's on the quiz. It's a quiz. That's the whole point. So, okay, for real. For the quizzes, it's hard to do free draw things because you would have to upload, and that creates a whole mess. So for the quizzes, you probably won't have to actually draw anything. For exams, however, because remember, exams are going to cover all of the chapters immediately before that exam. For the exams, there will be sections where you have to draw on your own, and so this is something that I could ask you to draw on an exam. Okay, let's keep going to sp3. So here's sp3. This is the situation that happens when we need to accommodate a central atom that needs to bond to 4 other atoms, or 3 other atoms with a lone pair, or 2 other atoms and 2 lone pairs. But this is what happens when we need to spread out 4 things around an atom. So we're going to combine all of our valence shell orbitals, our s and all of our p orbitals, and we'll get out this kind of balloon animal here, where it has 4 hybrids, sp3 orbital, 4 hybrid sp3 orbitals. Each of them are 109.5 degrees from each other, and this is going to give an overall Vesper geometry that's tetrahedral. So I want to show you guys, and this is just a reminder, this is true in all of these cases. This was a rule I told you guys about before, and it's still a rule now. The number of orbitals you put in when you're doing something, it has to equal the number of orbitals you get out. So we put in 4 atomic orbitals, and we got out 4 hybridized atomic orbitals. So I'm going to show you guys methane, which is an example of sp3 hybridization. It's the simplest example of sp3 hybridization. And in methane, of course, carbon has to bond to 4 hydrogens. So to spread those 4 hydrogens out as much as possible, we need our 4 hybrid orbitals. And I just want to point out the variety of ways that we can, that didn't work. I tried to figure out how to trigger the lights. Hang on, guys. Okay, for methane, we have all of these different ways to represent methane. We have like a ball and stick version up here. We've got a cartoon version of the bonding orbitals here. This one on the bottom right is called a space filling model, that it actually takes into account the size of the electron clouds and the atomic radii. On the far left over here, this is one where you can potentially see the geometry better, how the corners of a tetrahedral atom would create the corners of a pyramid shape. These are all different ways of representing the same thing. And I want to take a moment to point out that now we're going to turn a little bit of a corner where we're really going to need to pay attention to 3-dimensional space. We've been very much kind of stuck in Lewis structure world, where we flatten out molecules and make them fit on a page. Our molecules are coming alive now. So we're going to have ways that we'll learn in a slide a little bit later today, how to represent bonds that come out of the page with this wedge, and bonds that go behind the page with this dash. I'll come back to that concept. But these are all different ways of representing methane. Okay, so here's putting hybridization all together. Here's just a chart that's in your book. This came right out of your book, that shows you however many hybrid orbitals you need and what that hybridization pattern would be. It also gives the geometry here. Now keep in mind, this is the geometry for what's called the Vesper idealized geometry. This is the geometry assuming that all of the hybrid orbitals are involved in bonding. You have a few other geometries that are possible if some of those hybrid orbitals are housing lone pairs. So for example, You guys all know that water has a bent geometry. Well, it has a bent geometry because it's actually tetrahedral, but both of those lone pairs you don't really see. And so the geometry of the molecule that you see is bent, but the VSEPR geometry is tetrahedral. Okay, so here's again some similar examples for each of these hybridization statuses. Here's methane, which is sp3, ethylene, which is sp2 at each carbon, and acetylene, which is sp at each carbon. And then just to kind of pull it all together, I put down here at the bottom the same cartoon pictures we've been looking at for these hybridization options. Okay, so the next thing that I want to talk about is kind of what do we do about the double bond, right? So I told you that we're trying to describe the bonding of molecules here. And so the hybridization that we've just done does a really good job describing the sigma framework, but not the pi bonds. So the next couple of slides, we're going to take a look a little bit at that. So looking closer at ethylene, we just went over that each carbon atom in ethylene has bonds to 3 other atoms, and it does not have any lone pairs. So that means that each of the carbon atoms in ethylene has to be an sp2 hybridization state. And that means that you can draw out a bonding sketch of the sigma framework that looks like this in the upper left-hand corner, where you have each carbon atom that's sp2 hybridized. And then for each carbon atom, 2 of those hybrid orbitals are participating in the CH bond, and the third is participating with the other carbon's hybrid orbital to make a sigma bond between the 2 carbon atoms. And keep in mind also, all of these atoms, all 6 atoms and their entire bonding network for the sigma framework, they're in the plane of your screen, the way it's drawn right here. And that means that each of these carbon atoms has its 2 leftover unhybridized PZ orbitals that are sticking out of the screen and behind the screen. And so here is the pi bond representation. Now we're going to turn the molecule and look at it from a different angle. So this sigma bond framework is being represented as being perpendicular to your screen in this middle version. You can see the unhybridized leftover PZ orbitals on each of the carbon atoms, and that they're participating in a pi bond with each other, half above and half below the sigma bond plane framework. And then over here on the far right, we've got the balloon version of that same thing that I just described, where the purple and yellow orbitals represent the sigma bond framework, and all of those are perpendicular to the screen right now. And then the blue and the green represent the halves of the pi bonds that are above and below the plane created by that sigma bond network. I have a slide here for the bonding in acetylene. I want you guys to walk through this on your own after class, on your own time, and apply the same types of concepts that I just talked about for ethylene to acetylene. And just keep in mind that the py orbital and the pz orbital have to be 90 degrees to each other. So that is why our pi bonds in this triple bond are 90 degrees to each other. So in the last couple of minutes of class, I would like to go ahead and finish up chapter 1. It seems like a lot to cover, but don't worry, they're each only a slide or 2. I've already touched on the fact that we need to now start really thinking about 3-dimensional space. We're going to be moving away from the flat Lewis structure drawings. And so we're really going to need to be able to talk to each other, communicate with each other about the 3-dimensional aspects of molecules. And so here is ethane. That's just CH3, And in ethane, you can see immediately each of these carbon atoms is bonded to 4 things. That means each carbon atom is sp3 hybridized. And that means that each carbon atom might have 2 bonds in the plane of the page, but then it has to have bonds that are not in the plane of the page because of the nature of sp3 hybridization. It's tetrahedral, which means that it has to have things coming in and out of the plane. So I touched on this before, but this is going to be the notation that we use and that you guys need to know and start learning and start becoming familiar with. where we have a wedge bond that's coming out towards you and a dashed bond that's coming away from you. So in front of your screen and behind your screen. And everything that's just a regular straight line is understood by chemists to exist in the plane of the paper or the screen or whatever we're talking about. Okay. So here's something really important. If you guys zoned out, I want you to zone back in and pay attention to what I'm about to say. This is super duper duper important. That's why it's got a box around it. If you have a tetrahedral structure, you have to put the wedge and the dash next to each other, or else you have not actually unambiguously defined what's going on. So this example here, where the wedge and the dash are across from each other, it could actually represent two different molecules. If we were able to label the two hydrogens and keep track of which one's which, and the two methyl groups and keep track of which one's which, and I told you guys to go build this with a model kit, half of you would build one form and half of you would build a different form. You can't tell from this drawing, so you can't do it. You cannot put the wedge and the dash across from each other. In tetrahedral land, you have to put them next to each other, okay? It's not a complex concept, it's just a rule and a truth. All right, brief moment on bond rotation. We've been talking, I showed you in the other slide, ethane, which is CH3CH3. So in ethane, the bond between the two carbon atoms is a sigma bond only. That means the electron density is on the internuclear axis, so it's between the two nuclei. And that means that we have a possibility for free rotation. So I can take ethane and I can take the back methyl group, hold it still, and I can take the front methyl group and twist it like a doorknob, and it can rotate around. And the reason it can rotate around is because the carbon-carbon bond electron density is all in between those two carbon nuclei, like the axis on a car. And so you can rotate one side and not the other. Basically, it can rotate around this bond. But now contrast that. So this is an ethane where there's only a sigma bond between the two carbon atoms. Contrast that with ethylene, which we've seen already a couple of times today, that has a double bond between the two carbon atoms. So remember, a double bond is one sigma bond and one pi bond. So if we were to try to take our ethylene with its double bond, hold one side still, and twist the other side, we cannot do that. Double bonds cannot rotate freely the way that sigma bonds can, which means that double bonds cannot rotate freely, but single bonds can. So if you were to try to twist this, what you would do is you would move the orientation of one of those p orbitals, and when you do that, you would lessen and ultimately negate any chance that the two p orbitals have to overlap with each other. When you destroy that overlap, essentially you're breaking a bond. So you would be needing to put in energy into the system. And so double bonds don't have free rotation. Okay, in my last minute, I'm going to tell you briefly about isomerism. I will not quiz you on isomerism, but you are going to be responsible for it. So I encourage you to double check in the stuff on your book. But basically for right now, we're going to learn about just two kinds of isomers in chapter 1, and we'll revisit in chapter 5 and learn about all sorts of different kinds of stereoisomers besides the one we'll learn about today. But isomers in general are going to be molecules that have the same molecular formula, but might have different arrangements of how their atoms are. So this could be a different arrangement in the connectivity or how they're bonded together, in which case they're called constitutional isomers or structural isomers. Or it could be that they're bonded in the same kind of order, but the direction that they point in space is different, making them different molecules. I'll show you some examples briefly. In constitutional isomers, the easiest way to see these constitutional isomers is to look at the carbon scaffold and the branching or not branching. So here are all three of these examples are pentane, so C5. And linear N-pentane is different than isopentane, which has one branch, and that's different than neopentane, which has a bunch of branches. Okay, so these different connectivities are called constitutional isomers. And last slide. The last kind of isomer I'm going to talk to you guys about is a type of stereoisomer called geometric isomers. So these are cis and trans double bonds, which are geometric isomers with respect to each other. And in the cis case, you have groups on a double bond that are identical to each other on the same side of that double bond, versus a trans case, groups that are identical to each other are across or diagonal from each other on that double bond. And just a quick note here, you can see the difference between these cis-trans geometric isomers or stereoisomers and the constitutional isomers over here, because the connectivity is different. So all of these have the same molecular formula, but look over here at but-1-ene. We have a carbon here that has just 2 hydrogens attached. There's no carbon anywhere in trans-2-butene that has only 2 hydrogens attached. So we know that trans-2-butene and but-1-ene, those are constitutional isomers of each other. I'm gonna stop there, but that ends chapter 1. So thank you guys for sticking with me. I'm sorry I went a minute over, and I'll see you on Friday. And pay attention, I will put up an announcement about when I'll reschedule my office hours.
Thank you. Have a great weekend.
Thank you. Guys, I hope you guys all have a good weekend too, but don't forget we're meeting on Friday.
Sorry, I forgot.
And you have to come to class after you take the quiz.
True. Okay, have a great day.
Oh, I'm sorry, I got a question.
You guys have a great day too.
Excuse me, so I got a question.
Yeah, go ahead.
So about like a test on Friday, so it's gonna start at like 1 o'clock, or I have to come earlier?
So I'm gonna use class time to do the quiz. So if you take part of the class time, you'll log Canvas at 1 o'clock and take the quiz, but you have to be prompt, because after the quiz, and I'll start on chapter 2 for the rest of the class.
Okay. So a quiz takes around like 15 or 20 minutes?
Yeah, I haven't written it yet, so I haven't put in the timing on it yet, but you'll know in the instructions, and I'll send an announcement out with make sure everybody knows how to find the quiz, for example.
Okay, great. Thank you. Thank you so much.
Hi, Professor.
Hi.
On Monday, I was trying to come to your office hours, but it kept asking me to sign in, which I did with my VCU email for over 30 minutes, but it still didn't let me in. And I had sent you an email.
Yeah, I think I replied to your email, right?
But that's the link I used, but it still didn't let me in on Monday.
Yeah, so I don't know what was going on Monday, and I don't know, I've changed some of the settings, so I don't know if it's been fixed, because we haven't had a chance to try it. So I didn't know about that problem until after office hours were closed on Monday.
Okay. Then I'm going to try maybe next week, because I have another class at 3 today. Or in case I come back early and you're having your office hours, I'm going to try it again.
Okay, so this is Deborah that I'm talking to, right?
Yes.
I made an announcement right at the beginning of class. You might not have heard it, but I have to shift my office hours today.
Yes. Yeah, I was here. So I was